In this video, we're going to look at conjugate acid-base pairs and learn how to figure out what is the acid, what's the base, what's the conjugate acid, and what is the conjugate base. Okay, so we're going to start with looking at the Bronsted-Lowry definitions of acids and bases. This is going to help us determine what the acid is, what the base is. So the acid is defined as a proton, which is another word for hydrogen ion donor. So an acid is a proton donor and a base is a proton acceptor. And so you can have an acid-base reaction that involves the transfer of a hydrogen ion or a proton. And so we're going to look at what is going on with that proton, with that hydrogen ion. So when I say the word proton, think in your mind hydrogen ion and see where that hydrogen is going in the reaction. So let's get started with this example equation here. We have hydrocyanic acid reacting with the nitrite ion, and it produces cyanide ion and nitrous acid. Now you'll notice this is a weak acid-base reaction because we have a reaction arrow that is going in both directions. That means the forward reaction happens as well as the reverse reaction happens. And so by our definition of an acid being a proton donor, we can look at this, and we're going to be looking at the left-hand side first and looking at the species on the left and defining what they are. And so if our acid is a proton donor, we can look at these two things, and hydrocyanic acid is donating its hydrogen, this first hydrogen here, it donates it in the reaction when it becomes the cyanide ion, and it gives that hydrogen ion to the nitrite ion, and then nitrite ion becomes nitrous acid over here. So we can define this hydrocyanic acid as our acid because it is a hydrogen donor. This nitrite ion is going to be our base because it is a hydrogen ion acceptor. So we'll define that as a base. Now we can look at the reverse reaction because this is also an acid-base reaction. There is also a transfer of a hydrogen ion between the cyanide ion and the nitrous acid. In this reverse reaction, you have nitrous acid donating its proton, its hydrogen ion, to the cyanide ion when they become the species on the left. And so when we're defining what's on the right-hand side of the equation, these are going to be our conjugates. So this is our conjugate acid. It donates a proton, but it's on the right side, so it's our conjugate. And then cyanide ion here is going to be our conjugate base because it is our proton, our hydrogen ion acceptor in the reverse. And so we have this acid-base reaction. We have hydrocyanic acid and its conjugate base of the cyanide ion. And we have the nitrite ion, which is our base, and its conjugate acid of nitrous acid. So those are our conjugate acid-base pairs, and they differ by just a hydrogen ion. So if we write those out, our conjugate acid-base pairs consist of hydrocyanic acid with its conjugate of the cyanide ion. They differ by just a hydrogen ion. The other conjugate acid-base pair is the nitrite ion, which is the base, and its conjugate acid, which is nitrous acid, and they also differ by just a hydrogen ion. So your conjugate acid-base pairs are going to differ by just a hydrogen ion. Let's look at one more example. In this reaction, we have phosphoric acid reacting with ammonia to produce a dihydrogen phosphate ion and the ammonium ion. So again, we're going to look at what is going on here with the hydrogen ions. what is our hydrogen ion donor on the left side? We have phosphoric acid, and if we look at the species, it becomes, on the right, it becomes H2PO4, and so it lost a hydrogen ion in that. And so we can define this as our acid. Ammonia went from NH3 to NH4 with a +1 charge, and so the ammonia here gained a hydrogen ion in that reaction, and so we're going to define it as our base because it was a hydrogen ion acceptor. And so if we look at the reverse reaction and we look at this dihydrogen phosphate ion, in that reverse reaction, it gained a hydrogen ion. And so since it was a hydrogen ion acceptor, we would call this the conjugate base. And if we look at the ammonium ion, it went from NH4 with a plus charge to the other side, it went to a NH3. And so it lost a hydrogen ion in that process. And so this would be our conjugate acid. So just as a review, our phosphoric acid went from H2PO4 with a negative charge, and so it lost a hydrogen ion in that process, and so we define it as our acid. Ammonia went from NH3 to NH4, and so it gained a hydrogen ion in that process, and so by our definition, a proton or hydrogen ion acceptor is a base. And so then looking back, I don't know what happened to my arrow here. Okay, looking back, we have our H2PO4 with a negative charge, and in that reverse reaction, it became H3PO4, and so it gained a hydrogen ion in that, and our definition of base is a proton or hydrogen ion acceptor, and so H2PO4 dihydrogen phosphate ion is our conjugate base. And so we can write out our conjugate acid-base pairs as H3PO4 and H2PO4 with a negative charge. And so those two just differ by a hydrogen ion, which makes them our conjugate acid-base pair. Our other one then is ammonia and the ammonium ion. They differ also by just a hydrogen ion. And so those are, remember, our conjugate acid pairs are just going to differ by a hydrogen ion. And so that just is a brief example of a couple of reactions of how to define the acid, the base, the conjugate acid, and the conjugate base. And it all goes back to our definition of what an acid is and what a base is. So make sure you keep those definitions in mind when you are trying to identify acid-base pairs.